Hey there and welcome. Today we are on the hunt for energy. Seriously, we're going to follow every single joule as it travels through the world of electromagnetic induction, all the way from a simple push to the final burst of heat. All right, let's kick things off with a classic physics puzzle. Picture this. You push a magnet toward a coil of wire. Now, Lenz's law kicks in, and the coil pushes right back at you. You're putting in work to overcome that resistance. So where does all that energy you're spending actually go? And listen, this isn't just some abstract thought experiment. This exact question is the key to cracking some of the most common questions you'll see on your exams. So let's solve this thing. We're going to draw up an energy map and follow that trail step by step. So to tackle any of these energy mysteries, you absolutely need a map. But here's the best part. The path is always the same. It's like a universal cheat code. Once you get it, you can use it on pretty much any electromagnetic induction problem they throw at you. And here it is. It's a really simple three-step journey. First, you've got your mechanical work. That's your push. That gets converted into electrical energy, which shows up as an induced current. Then, that current has to flow through the wire, which has some resistance, right? And just like in any circuit, that struggle creates thermal energy. The wire heats up. So it's always mechanical to electrical to thermal. That's the path. Here's a great way to think about it. Imagine that pushback you feel from Lenz's law is like a kind of magnetic friction. The effort you put in to overcome this friction is what generates the electricity. And that electricity, it basically powers a tiny, tiny heater, which is just the resistor in the coil. See? Energy isn't being created or destroyed here. It's just being perfectly transformed from one form to another. And this energy map, it's not just for this one specific case. Oh no, it's your go-to tool for every key scenario you'll run into. Whether you're pushing a magnet toward a coil, sliding a rod on conducting rails, or even just building up a current in an inductor, they all follow this exact same energy trail. It's super reliable. Okay, first case up, let's put our new map to the test and use it to prove something really fundamental. That Lenz's law is basically just another way of stating the law of conservation of energy. And here's the kind of question you can expect, pulled right from a CBSE quiz. Justify. Lenz's law is a consequence of the law of conservation of energy. So what they're really asking you to do is connect this simple rule about current direction to, well, one of the biggest, most important laws in all of physics. No pressure. Okay, to really nail this answer, let's imagine two different universes. First, on the left, let's visit a bizarro universe where Lenz's law doesn't exist. Here, the induced current actually helps the motion. So you give the magnet a tiny nudge, it gets attracted, which makes it speed up, creating even more current, which creates more attraction. You see where this is going? It would accelerate forever. You've just created a perpetual motion machine, free energy from nothing, which, is completely impossible. Now let's come back to our universe on the right. Here, Lenz's law makes sure the current opposes the change. The magnet gets repelled. So if you want to move it, you have to do work, and that work is what gets converted into electrical energy. Everything balances. Physics, thankfully, works. So for the exam, here is your perfect 3-mark answer structure. Step 1, just state the law. The induced current always opposes the change that causes it. Simple. Step 2, explain why the opposite isn't possible. You just say, hey, if it aided the change, you get acceleration without work, which violates the law of conservation of energy. And step 3, connect it all back to our energy map. Opposition requires you to do mechanical work. That work gets converted to electrical energy and finally to heat. Energy is transformed, not created. Boom, full marks. All right, next stop on our energy tour. So what about a different scenario? What if you're not moving a magnet at all? What if you're just, say, building up a current inside an inductor? Where does the energy go in that case? Well, it doesn't just instantly turn into heat. Instead, it gets stored. See, when you try to push current into an inductor, the inductor fights back. It creates its own opposing voltage, which we call a back EMF. But the work you do to overcome that pushback isn't wasted. Nope, it gets saved up, stored as potential energy right inside the inductor's magnetic field. And the formula to calculate exactly how much energy is stored is U equals 1/2 Li squared. Let's plug in some real numbers from a quiz question to see this in action. Say you have a big inductor, 8.0 henries, and you build up a current of 0.10 amps. You run the numbers through the formula, and bam, you find that you've stored exactly zero point zero 0.04 joules of energy in that magnetic field. It's that straightforward. Okay, quick warning. Exam trap alert. I'm telling you, it is so easy to forget that 1/2 in the formula. Examiners know this, and they love to catch people on it. So burn this into your brain. The energy stored is 1/2 Li squared. Don't be that person who loses easy marks. All right, for our final case, let's look at the motional EMF setup. This one is beautiful because it brings everything we've talked about together. It's like a perfect energy balance sheet where we can mathematically connect the force you put in with the power that comes out. So the question is a two-parter. First, you have to figure out the external force needed to push a conducting rod at a constant speed. Then, and this is the cool part, you have to prove with the math that the mechanical power you're putting in is exactly the same as the electrical power turning into heat. So let's just walk through the logic. First, the rod moves through the magnetic field, which creates a voltage. That's our motional EMF. That voltage drives a current. Now, because there's a current, Lenz's law creates a magnetic drag force pulling it backward. Step 2. To keep it moving at a constant speed, your push forward has to perfectly cancel out that magnetic drag. Step 3. We can calculate the mechanical power you're putting in. That's just your force times the velocity. And for the final step, we calculate the electrical power being lost as heat in the resistor, using I squared R. And what do you find? This is the beautiful part. The final equation for the mechanical power you put in is identical to the equation for the electrical power that's dissipated as heat. They're not just close, they are exactly equal. The energy books are perfectly balanced, down to the very last joule. The work your hand is doing is being converted into heat in that resistor at the exact same rate. It's perfect. So let's circle all the way back to that first mystery we started with. Where did the energy from your push actually go? Well, now we know. We followed those joules on their complete journey, from start to finish. And if there's one thing to take away from all this, it's that Lenz's law isn't just some random rule about directions. It's basically nature's accountant. It's the physical law that guarantees you can't get something for nothing. It is the no free lunch rule of the universe, and it makes sure that energy is always perfectly conserved. So by following this energy trail with us today, you haven't just learned a concept, you've built a really powerful framework, a way of thinking that's going to help you ace those key questions on your exam, like Q11, Q12, and Q15. From now on, whenever you see one of these problems, just ask yourself one simple question: where does the energy go? If you can answer that, you'll always find your way to the right answer.